welcome to the lecture of this finite volume method. Now, further in the absence of any source term, in the absence of any source term, the multidimensional heat conduction equation, the multidimensional equation reduced to this equation, delta dot gamma phi equals to 0. So, this implies that phi, and that implies straightway one important property, phi or phi plus some constant are the solution of these particular Gauni equations. Since this is an elliptical system, the solution of this equation would be same whether it is a phi or it is a phi plus any constant. A constant discretization method should reflect this property, or rather the important property of a consistent discretization method must depict this property, which is one of the characteristics of a solution to a elliptical PDEs. So, this is very important, and what this happens once the discretization method has to reflect this property, this discretized equation must satisfy the following criteria. What is that? It should have AC phi c plus summation of f NBC capital F phi f equals to 0, or AC phi c plus some C1 constant plus summation of f NBC phi f AF phi f plus C1 must be 0. So, that means where C1 is any arbitrary constant, okay, which will lead to essentially AC plus F NBC AF phi f have AF equals to 0. So, this has to be satisfied by the consistent discretized equation. So, this is valid, one has to note that this is only valid, please note this is valid for the system without source or sink term. So, this is very important, that without that this is valid. Valid for system without or with or without source and sink term. So, this if I rewrite, this can be rewritten as AC equals to minus summation F NBC equals to AF, or one can write these things as F NBC AF divided by AC equals to -1. So, which means one can see this particular equation tells a very important criteria that phi c is the weighted sum of its neighbor, essentially which tells that phi c can be seen as weighted sum of its neighbors. Okay. And in absence of any source term, it is always be bounded by the neighboring values. Okay. So, this important equation which clearly one can infer that phi c must be looking at as a weighted average or sum of its neighboring elements, and it remains always bounded by the neighboring values like phi f. So, whether it is east or west, so they actually. Now, if a source term is present, so we got a very nice criteria for in the absence of source or string term, but if there is a source term which is present there in the system, that means where SC phi not equals to 0. So, then phi c does not need to be bounded in this fashion. Okay. And it can over or undershoot the neighboring values. So, now one can immediately ask that when I have a source term, so phi c does not need to be bounded in a particular fashion. Fashion is that in this particular fashion. So, repeatedly this is mentioned that, or I am reiterating the fact that this is only true when there is no source or string term. Okay. Now, phi c, if there is a source term, then this need not to be bounded through that particular equation. At the same time, the phi c could overshoot or undershoot from his neighboring values. Now, one may immediately think that is this physical, but when there is a source or string term, this is absolutely physical phenomena. So, this is possible. Okay. So, which gets you an important message that when you have this assumption of the linear profiles, it comes with certain restriction, but if you keep on refining your grid, this does not have significant impact on the results. Now, at the same time, if someone uses higher order profile, then one has to be careful whether the system has any source or sink term. If the system does not have any source or sink term, then the higher order assumption can overshoot the values at the faces, which is unphysical, as we have seen, and the values should be satisfied with this kind of criteria. Now, this criteria is also valid for the situation or the equation system where you have the or one has source or sink term, but in that case things can overshoot, and which is perfectly fine. Now, having said that, one more important thing to note here is that coefficients, the sign of AC and AF, if you look at, they are in opposite nature. So, this is also physical. Why? Because this has a complete physical meaning, because the value of phi A, the value of phi A can increase or decrease, or the rather if phi f is increasing, then which will lead to phi c to increase. If phi f is decreasing, then this also do in the other way around. Okay. So, this has a physical meaning that the signs, opposite signs are of physical nature. This also other way one can think about, this has to do with the boundedness of the nature. So, the boundedness is actually doing that thing. If one goes down, other goes up, in one goes up, other one goes down, and that has a complete physical significance. So, one can think that this particular property comes inherently as a part of your discretized equation, one discretized equation. One need not to forcefully enforce these particular properties. Okay. So, these are some important systems that one can. Now, once you get that discretized system, if you just go back, this particular system, your AC and AF. So, this is my system, AC phi c summation of AF NBC phi f AF equals to BC. That is my discretized equation system. Now, once you get that discretized equation system, you can always find out the coefficients, but you need to impose boundary condition, and this equation is only valid for any interior elements, it is not true for any boundary elements. So, the boundary elements needs to be treated separately. Now, boundary conditions could be of different type, and we can see how the boundary elements are imposed now on the system. So, you can think about that you have this particular, let us say, system, you get this, you get these elements, okay, and this is your C, this is your S, this is your southwest, west, northwest, north, and this line is my boundary line, okay. So, you have this flux going this way, and then here is a point, boundary point, where this would be SB, okay. So, you can think about this side is your boundary side, and now if you have that, so this distance would be a distance of delta x small b, and rest remains same as per our notation. Now, for the boundary also, what we need to do? We need to put the same system of equation. This is our equation system equals to QC BC. So, that is still, this is my governing equation, this must be valid, but the one which we got here, this is only valid. So, there is a difference. What we are starting, that this is valid with any interior element. Why? Because this requires some surrounding elements, and that is where the validity comes from. But when we start from here, then we will get the equation system from at that particular boundary, where you say that my JB, if you apply this equation at boundary B, then this would be JB dot SB equals to flux TB, which will be minus gamma B delta phi B dot SB, which is nothing but flux CB, flux C plus flux BB. Now, the specification of boundary condition will be different. So, number 1, it could be Dirichlet condition. So, which means you have specified phi equals to phi B is phi specified. So, at this phase I am saying that phi B equals to specified, that means this is known. So, this is my Dirichlet condition or constant boundary condition. So, once I say that at that phase phi B is known, then I can use that condition and write my total flux. At B, my flux TB is minus gamma B del phi B dot SB, which is going to be my minus gamma B SB divided by d CB phi B minus phi C. So, that is equivalent to flux CB phi C plus flux VB, which will get you, which implies that flux CB equals to gamma B dB, let us say small ab, and flux VB equals to minus gamma B dB and phi b, which is minus AB phi b, where your dB is defined as SB by dCB. Okay. So, if you look at this particular element shown here in this particular figure, the coefficients at east face, that is AE, which is essentially 0, and the discretized equation would yield like AC phi C plus AW phi W plus AN phi N plus AS phi S equals to BC. So, if you compare with your this equation, the complete equation which you got, this is my complete equation for any interior element, where you have AC phi C, AE phi E, AW phi E, AN phi N, AS. So, that means in one interior cell has all these east, south, west, north element. So, that is the governing equation. Now, in this particular case, distillate boundary condition, it boils down to a different equation. Why? This particular cell and this particular face, this is essentially east, theoretically east face, and the east face is exposed to the given boundary condition, and other elements like north, west or south, they are there as it is. So, your east coefficient goes up and you get back this system, where essentially if you write it down, AW phi W plus AN phi N plus AS phi S equals to BC, where your AE is 0, AW equals to flux FW equals to minus gamma W dW. Similarly, AN equals to flux Fn, which is minus gamma n dN. AS is flux Fs, which is gamma S ds, and AC equals to flux Cb plus small f goes from all the faces, flux Cf, which is nothing but flux Cb plus flux Cw plus flux Cn plus flux Cs. So, that is what you get, and the BC is the source term, which is QC BC minus flux VB plus summation of NBC and flux VF. So, this is what you get for the given distillate condition. So, one can note few comments. So, some important comments or observation. Number 1 is that the coefficient AB is larger than other neighbor coefficients because B is closer to C and consequently has more influence on phi C. Okay. So, second is the coefficient AC is still the sum of all neighboring elements or neighboring coefficients including AB. This means important criteria means for the boundary element this F, which is the criteria mod of AF divided by mod of AC less than 1 gives the second necessary condition to satisfy Scarborough criteria. So, this is second observation. Okay. And the third one would be, so this criteria, the Scarborough criteria would be achieved through the iteration, and the third one is that the product AB phi B, which is the product essentially equivalent to your flux VB, is now on the right hand side of the equation, is on the right hand side of the equation and part of BC, and the reason is that because it now contains no unknowns. Okay. So, there are three very important observations one can make out of this distillate boundary condition implementation. So, this is my system that I obtain and these are my coefficients. So, one of the important observation is that AB is larger than the other neighboring coefficients because B is closer to C. So, it will have more impact on the element C. Then the Scarborough criteria is also satisfied through iteration, and the third one is that now the product AB phi B, which is flux VB, is sitting on the right hand side of the equation because it is no more unknown, all the terms has known values. So, this is where how one can treat the specified boundary condition. So, we will look at the other boundary conditions in the subsequent lectures. Thank you.